Here's something real quick. You guys have a good weekend? Wasn't quite as snowpocalypsey outside. Not so bad. My daughter was excited on the way to the bus stop this morning. She said, "Mom, look, it's not ice anymore. It's just slush." And I still like twisted my ankle on the slush. Oh well, what are you gonna do? I don't know. I tried. Whew. Okay, so what do you guys think of these problems? Are they reasonably okay at this point? Like a lot of it looks familiar, right? Because we're just kind of building off of things that we've already done. I always kind of enjoyed this problem because this is a real life situation. Have you guys ever had a situation like this happen to you? Where you go to pick up your grocery bag and it just rips out at the bottom. I hate it when that happens. And a lot of the time, honestly, I think there's already a hole in the bag. I've seen that every once in a while. Cheap bags, yeah. And then I actually invested in like nice reusable grocery bags. And then with the whole coronavirus thing, everybody was like, you can't take your reusable bags to the grocery store. They might get coronavirus on them. I think that that's very unlikely. Like, you're not going to get so much coronavirus on it that by picking up your grocery bag, you're going to get coronavirus. But I still haven't used them in like a year. It's so sad because I really like my reusable bags. Anyway, so for this problem, we are looking at a situation where we are trying to figure out how if the groceries could stay in the bag. It also implies kind of an interesting idea is that if you lift the bag up slowly, it can actually support more weight than if you rip it up or pick it up all at once, because that quicker acceleration means that you have to have more force applied to it, which kind of makes sense. You know, if you pick up something slowly, it's more likely to stay intact. Have you guys ever lifted up something very carefully, like if it's sitting on a piece of paper or tissue or something and carried it around? Anyway, it says the maximum force that a grocery bag can withstand without ripping is 250 newtons. So that's an important number. Suppose that the bag is filled with 20 kilograms of groceries and lifted with an acceleration of 5 meters per second squared. Do the groceries stay in the bag? So that's the first thing we have to answer. The second thing we have to do, it says make a quantitative force diagram, write a net force equation for the axis along which the forces are not balanced. So I'm going to start with a force diagram. For this, I'm going to focus on the groceries. I know that there was a little bit of debate in some classes about do we focus on the bag or do we focus on the groceries? Well, since we're talking about the mass of the groceries, I think that it makes sense to look at the force on the groceries because the bag is going to be holding the groceries up and gravity is going to be pulling the groceries down, and those are the forces that we're interested in looking at. So for our force diagram, we're going to start with a point to indicate what our center of mass is. We know that we have a force due to gravity on our groceries downward, and that we have what is basically a normal force upward on the groceries by the bag. And we can start to quantify some of these. It says the maximum force a grocery bag can withstand without ripping is 250 newtons. That's this upward normal force. 250 newtons up. We're also told that the bag is filled with groceries that weigh 20 kilograms. Well, 20 kilograms means that we are looking at it's multiplication. We are looking at a downward force of 200 newtons. Sorry, minus 200 newtons because it's downward. So there's my force diagram, and it's quantitative. It includes the numbers. So I got that. Then it says write a net force equation for the axis along which forces are not balanced. So our net force equation, as always, is going to be equal to the mass times the acceleration, which is going to be equal to the sum of our forces. So far, so good? Are you guys doing this part out of habit yet? That's a good habit. Okay, so next we have to figure out, do the groceries stay in the bag? Well, we're told that the bag is lifted with an acceleration of 5 meters per second squared. So if we have 20 kilograms and they are lifted at 5 meters per second squared, then the total force there is going to be 5 times 20 is 100 newtons upward. So if we pick it up and the bag has to be able to withstand the is this number greater than or less than this number? What's the maximum acceleration we could use for our groceries before the bag rips? We can figure that out, right? So let's not go this way. Let's go the other way. We're going to figure out our maximum acceleration. Mass times maximum acceleration, Fn plus Fg. So our mass here is 20 kilograms times that acceleration. We're going to see how close that is to 5 meters per second squared. If it's smaller than that, then our bag's going to rip, right? It means we have to be more careful with it. Our normal force here is 250 newtons. Our force due to gravity is 200. So this is going to be 20 kilograms times our acceleration is equal to just 50 newtons. So this is going to be 2.5 meters per second squared. That's the fastest we can lift our groceries without the bag breaking. Can we lift them with 5 meters per second squared of acceleration? We could try, but we'd break the bag, right? Oh no. I'm going to change that to at. That would be much too hard of a yank on our groceries. Would not be a good idea. What questions do you guys have about that one? If we did it this way, that's the most upward force that we could manage. Sorry, most downward that we could handle at that. I have to think about this for a second. What do we actually solve there? It's much less than 250, right? 250, we're never going to get there. Yeah, it makes sense, but we'll get there. Do it this way. So we found the acceleration. When we compare it to this, we know that it's definitely going to break. For sure, that's a problem. Okay, do you guys have any questions about number 2? Okay. Number 3. Come on, camera. A student standing on a scale in an elevator at rest sees his weight is 240 newtons. I think I already did this one. As the elevator rises, the scale reading increases to 150 newtons and then returns to normal. Why does it increase? What happens? Well, why does the scale reading increase though? Because gravity shouldn't change, right? Gravity is always the mass of an object times acceleration due to gravity. So what is the scale doing? What's it doing when you stand on it? You guys know how scales work? Yeah? I mean, you stand on it, it gives you a number, right? But what does that number mean? So with a scale, if you are, let me just sketch this here. If you have a little scale, right? We're gonna break this down a little bit. Sometimes there's a spring under here. It's different kinds of mechanisms. But if you stand on a scale, I'm gonna put a box on the scale, right? You don't need to make it a complicated shape, just make it a box. If I've got a box on a scale, it's gonna have it's gonna exert a force downward from gravity. And then the other force on that box is a normal force from the scale, right? And so what happens is that if you change your acceleration vertically, it's going to change what the reading on the scale has to be. So if If the floor of the elevator is pushing upward on somebody, that's going to change the acceleration. And if that floor is moving downward with the person, that's going to change their acceleration too. And so whenever we're looking at these scales and we see a difference between the weight, which is Fg, right? Remember, weight's not mass. Weight is force due to gravity. And then what the scale is saying, it's telling us that these two forces are not balanced anymore. And it can tell us what direction they're not balanced. If the scale reading is higher, then that means that the scale is going upward because it's pushing more on the person and it's going to make them go up. If the scale is not pushing as much on the person, then that means that the downward force is going to be greater than the upward force. No, that's not right either. It means that the magnitude is going to be a little bit less. And so you're going to see the person going downward. Okay, so what I want you guys to notice about this problem, though, is there's basically 3 different points. One is as the elevator rises, this part right here. The elevator rises is one part. The scale reading increases and then returns to normal. And then the elevator slows to a stop. So returns to normal is the second part. And then slows to a stop is the third part. And so we're actually going to be looking at 3 different force diagrams to be able to figure this out. We are asked to determine the acceleration at the beginning and end of the trip, make quantitative force diagrams, see how this is diagrams, and then write net force equations where they're not balanced. So we're going to have part 1, rising, part 2, the return to normal, and then 3, slows to a stop. Where do we have accelerations happening here? Changes in speed. Escalators don't have change in speed, right? Escalators, little steps that move, because they're always going on the same speed, and you jump on them. Elevators, luckily, are not that way. Can you imagine if they were? If it just kind of like went up and like went around in a circle or something, you had to jump on it. That would be horrifying. That would be terrible. So where we see accelerations are here where it starts to rise. Right here starts, right? Because you're going to start from a position where there's no motion, and then you're going to speed up. And so since we're speeding up, that's where we have a change in velocity. And then here we've got to slow down. And so here we've got another change in velocity. So those are the points where we're expecting to have a non-zero acceleration. When we're moving at a normal speed, are we going to have acceleration? Is your elevator speeding up the entire time you're on it? You guys have ridden elevators before, right? Some of you, I'm not sure. Or it's just Monday morning and we're tired. So for this return to normal, this is where we're going to have a constant velocity. Constant velocity. Okay, so at the beginning, where we're starting, we have a guy that's standing on an elevator, and it has to speed up. So it's going to accelerate. And we know that the force due to gravity here for a person who, let's see, well, they're 84 kilograms, but it says 840 newtons, right? That's his weight. So this is 840 kilograms. Sorry, newtons. Whew. And the scale says 1050. That's a little bit bigger than this, right? 1050 newtons. Normal force on the person by the scale that's on the floor of the elevator, right? When it returns to normal, we're going to notice that we have the correct force on the scale. So our Fg, our minus 840, is going to be the same as the upward force that we're reading on our scale, 840. When our elevator is slowing down, When it's slowing down, we're going to notice that we've got gravity minus 840, and the elevator, the upward force of the elevator on the person is only going to be 588 newtons. So it changes. For our net force equations, we're going to have our net force equals mass times acceleration, which is equal to the sum of our forces. It's all the same equation all the way across there. The only thing that changes is the values that we put into it. We were asked, after we make our quantitative force diagrams and our net force equations, we are also asked at the very beginning here, determine the acceleration at the beginning and end of the trip. We know that here, right, if the sum of these two forces is 0, that acceleration must also be 0. So we know that if the weight is 840 newtons, that our mass must be 84 kilograms. So down here we'd have 84 kilograms times acceleration equals 840 minus 840. So our acceleration is 0 meters per second squared. We're at a constant speed. It doesn't mean we're not moving. It just means our speed isn't changing. For these on either side, our mass is 84 kilograms times the acceleration, which is what we want to solve for. Here our normal force is greater than our force due to gravity. So what that means is that if we find the difference between those, it's 210 newtons. And our acceleration then here is going to be 2.5 meters per second squared, is what I got. It's accelerating upward because the upward force is greater than the downward force. So that's what happens when he speeds up. On the other side, if we do the same thing, we find that our 84 kilogram mass times our acceleration, the thing we want to find, is going to be equal to, which way do I want to do this? 588 newtons minus 840 newtons. So 84 kilograms times acceleration is equal to minus 252 newtons. So here our acceleration is going to be minus 3 meters per second squared, which means we're accelerating downward, which means we're slowing down. Each second we're going a little bit slower than the second before. What questions do you guys have about number 3? I think the trickiest part to that is recognizing that you need to actually do it in more than one part. You can't just make it a single thing. Oh, the other thing, draw a motion map. How many of you guys drew a motion map? Yeah, some of you guys saw it there. Okay. So the motion map should look something like at the bottom floor. Let's see, at the bottom floor, you start out slowly. So you start with your dots close together and then they spread out. And then, so I call this part 1, right? It goes with this part. Then you're going to go at a constant velocity for a little bit of time. And then you have to slow down. And when you slow down, your dots are going to get a little bit closer together. And for all the bells and whistles, you need arrows that go about halfway between the dots. And it's kind of labeled because I put floor and then I put stop, but I'm going to put T equals 0 down here. Okay. Any questions about number 3? How'd you guys do? Okay? Mostly okay? You can have a thumbs up if you did mostly okay. All right. Last one, number 4. A sign in an elevator states that the maximum occupancy is 20 people. I don't know about you guys. I get nervous when I see 20 people in an elevator. Suppose that the safety engineers assume the mass of the average rider is 75 kilograms. Let's see. For those of us who live in the United States, 75 kilograms. Do you guys know your weight, your mass in kilograms? You don't have to yell it out, by the way. 75 kilograms to pounds. It's 165 pounds. The elevator itself has a mass of 500 kilograms. The cable supporting the elevator can tolerate a maximum force of 30,000 newtons. That sounds like a lot, right? How many kilograms is that? That's going to be about 3,000 kilograms. I want to know how much that would be in pounds. It gave me pounds to kilograms. Kg to pounds. This is about 6,614 pounds. What's the greatest acceleration the elevator's motor can produce without snapping the cable? So this is the thing that we actually want to figure out. The greatest acceleration without snapping the cable. We need to make a force diagram, write a net force equation. Here we go. Our elevator. So here is our elevator. We figured out, let's see. We need to know what the mass of our elevator is plus people. So to do that, we've got 20 people times 75 kilograms per person plus the 500 kilograms for the elevator. So if we do that and add it together, we find that that has a mass of 2,000 kilograms. We know that if we've got a mass of 2,000 kilograms, that the downward force due to gravity is going to be 10 times that. That's going to be minus 20,000 newtons of force, just to hold it. We know that the most force that our elevator can hold is 30,000 newtons. So if there's tension on this cable, the greatest that it can be is going to be 30,000. So I put a greater, let's see, a less than sign there to show that 30,000 was the most that it could hold. So if I want to solve for what the acceleration would be if it was 30,000, the most it could hold, I'm going to start with my net force equation. Net force equals the mass times the acceleration, which is equal to the sum of my two forces. So our mass here is 2,000 kilograms times our acceleration equals 30,000 newtons minus 20,000. Whoops, sorry about that. Newtons. So I've got 2,000 kilograms times acceleration equals 10,000 newtons. That's my difference between the two. So my acceleration, my biggest acceleration can be 5 meters per second squared, which means this is the most my elevator can accelerate. Can it hold all 30,000 people, or all 30,000, or all 20,000 newtons of force? It can go higher than that, right? If our elevator was just hanging there and not moving, we could figure out how much that would hold too, right? Because we could take our 30,000 newtons minus the mass of the elevator, which is 50. And if we assume the same thing with the average rider, 75 kilograms, we find that this thing, that's not right. It's not going to hold 400 people. Oh, I know what I did. It's going to be 40 people. So if we do our 30,000, we're going to figure out how much mass that is. So I'm going to divide it by 10. So I can hold a total amount of mass of 3,000 kilograms of mass. I've got 500 that's allocated just towards the mass of the elevator. And then I'm going to divide that by 75 kilograms per person. So this thing could actually hold 33 people. If I have 33 people in my elevator instead of 20, what's that going to do to my acceleration? Have I left room for acceleration there? I haven't. Have you guys ever noticed that sometimes elevators that have lots of people don't seem to accelerate as much as ones that only have one person in them? Just pay attention to that next time you ride an elevator. So there's a force that's going to be applied to the cable on the elevator, and how fast it moves is going to depend on how many people are in the elevator. It's kind of an interesting thing. Okay, do you guys have any questions about number 4? How are you guys feeling about this stuff? Still okay? Okay. So we've got not a lot of time left. Where we're headed next is we're going to start doing something that's a little bit different. I think we might not start this day, but I'm going to say a few words about it. So tomorrow you guys have the ACT test. I'm not sure how much stuff you're going to see on it from physics class, but keep in mind that if you do encounter problems where you have to solve for something, that you think about what the values are that are required and which ones actually have relationships with each other. Because I know sometimes on tests like the SAT, they like to give you extra information that doesn't really apply to what you're doing. But what we're going to start doing after we get back is combining kinematics. Remember motion stuff? I know it's been a little while, hasn't it? But we're going to start looking at the equations for moving things like that we used in the first couple of units, and combining that with our Newton's second law, because we have a tie there, right? We have acceleration. So acceleration is the thing that's going to tie these two things together. When we did kinematics, we said the thing that all the equations had in common was time. And now what we have is a connection between forces and motion, where we can start to use them to say things about the motion of objects, which I think is pretty cool. Okay, so you guys have any other questions for me? Do you guys have questions about the ACT? I'm not an ACT expert. Sorry. Pay attention to graphs. They like to give you graphs. Yeah. And I would recommend, if you do a problem and you're not 100% sure on it, that you double check it, because I know when they write that test, sometimes they will solve it in the most common wrong way, and that answer will be there available too. And so just make sure that if you're between two different possible ways to solve something, that if you have time to try them both, because one of them might be correct, even if your first stab at it gives you an answer that's available. Anyway. Okay, so I think we're gonna be done a little bit early today, but I'm okay with that. We have about 8 minutes left in class. So if you have any questions, just let me know, okay? Yes, sir. Yeah, you can go back.